This is lesson 24, the penultimate lesson before we end this thing. Let me share my screen or my window. I think that's what I want. So hopefully you can see my notebook. These are my notes on lesson 24, and they're somewhat scattered in the sense that parts that I thought were just kind of going over things again, I was hit very lightly, and I hit kind of more heavily the transform or the attention, and also before that the sinusoidal encoding. Did everybody watch the lecture?
I
The
didn't.
I watched it. I watched it the last half hour or so. I kind of glazed over. So like the conditional
Okay, no
stuff
worries.
was not super clear for me.
Okay, well, I do have some more detail on that, so that will be. I actually focused more on that than I did, maybe not more on that, but I focused more on that part of it than I did on the very long beginning part.
No, okay,
Because in the
good.
very long beginning part, he's talking about rebuilding again the UNet, the diffusion UNet that's already been done basically from last time, but putting together now, not for doing a categorization, but for doing the stable diffusion, right? So, and he also makes it the same size as the stable diffusion model, so it's a bigger model. So at this we'll have supposedly we'll have everything. He says at that point we'll have everything except for attention, which we will do later. And what he doesn't say is we also won't have the latent layers, right? So this is remember stable diffusion is actually a latent diffusion model. So we're still doing the diffusion at the image level. And so one of the big wins in the stable diffusion is doing it at the latent level. And I hope we're going to do that for the final lesson next week. I don't know yet. One thing I did see for the next lesson next week that I'm looking forward to is the music generative AI. So
Yeah, me too.
yeah, I like that kind of thing. So the other thing, let's see, latent diffusion, tension. Oh, and the other thing was the stable diffusion is also conditioned on like full sentences, and this is just conditioned at the end of this lesson. We'll condition on just the category. So you can say, "Give me t-shirts," because that's one of the categories of the MNIST fashion thing. Okay, so that's it. Some other highlights. I noted here that he does the downsampling, and now he separates out the res blocks, and so he does the sampling of the separate or downsampling of the separate conv layer that downsamples stride 2. And for upsampling, he also does just a regular res block and then does an neural network torch upsampling thing, which just copies the pixels. So it takes one pixel, makes it into a 2x2, and then he does a convolution to mix those together, stride 1 convolution. And the other kind of thing he goes off on is the saved mix-in thing, which was another way to to kind of automatically save the cross connections for the UNet. Right? That's one of the big things with the UNet is these residual connections across from the input layer of the same dimension to the output layer. And he uses mix-ins for that. I don't usually use these things. They rely heavily on Python's method resolution order, which is something that if you don't do multiple inheritance, you don't worry about. And especially if you don't do implementation inheritance, which I also avoid and abhor, you won't worry about it either. But it has to do with the fact when a Python class inherits from more than one superclass, the question is if the method is defined in both superclasses, which one goes first? And it turns out it depends on the order in which you define the superclass. So here, in fact, I won't even go into it in detail. He's just using it as a tool to, unless you guys are interested in this.
I mean I've come across mixins in the past. It's not something I'm really super familiar with though. But yeah, I mean I thought it was cool doing a brief review of it. So I mean
yeah, okay. So if you define this class A, it does nothing else but calls a super as often they will. I define it's only a callable class. Stop tool tipping. It's a callable class, and it when you call it, it first calls the super, and then it prints A. And then class B here just prints B. It doesn't call super at all. So we define a new class C, which inherits from A and B in that order. Then when I call, well, first of all, this first part, this is just creating, it's kind of confusing. This part is just creating the object, the instance C. So that calls init, but there is no init, so it doesn't do anything. Then we're going to call instance C. So what it'll actually will do is first call A, which is, that's the super, the first superclass. And then, well, not first, it will only call the first one because that's method resolution order. If it exists in A, I'm going to call that one. Meanwhile, in A, when it calls super, it actually knows that this class has two superclasses, and instead of going to an upper class, it goes to the brother classes or the sibling class B and call its super method. So that's how this mix-in. And so you can see if I do this, I get B and then I get A, which is what you'd expect because I get B from calling class. Sorry, I get B from calling the super, and then A from calling the printing A from the first thing. And so the trick there is to define a class A, which does overrides what you wanted to have happen in B, or wraps it more likely, right? Then you can call super within the class A, and it will actually end up calling what was in class B. And he uses that to define the saved class, which does nothing other than the multiple inheritance, right?
Right, right.
Well, the saved class itself does something. It saves the things, but then you then define saved embedding network, whatever, and then saved embedding ResNet, or saved ResNet, I should say. The embedding comes later. Saved ResNet, and that thing does nothing. It's just passed, but it's just because its two parents are in that order. So anyway, that was a long explanation of that. Whoa, is that me echoing around? No, that's. Is that a year? Yeah.
I'm hearing some background stuff too. I don't think it was me. I have a dog barking in the background, so I'm trying to mute myself here.
I'm not sure. Maybe it's me because I don't hear it.
Okay, it's gone now. That was weird. Maybe it was the people that run Zoom eavesdropping. What are these guys doing? Okay, where was I at? So now we are. So now the next problem is that we want to have this thing learn about the time, because we have to pass the time in, right? To the. Oh no, what was the point of this time embedding now? Yes, right. Sorry, I confused myself here. So the next thing was to pass in this the time of the time being the beta, basically how much noise you put in into the model, so it can learn from that as well. And for this, he uses an embedding for the time, and you remember from how embeddings work before. Usually they're learned embeddings. You can think of them as being a learned embedding as being like a one hot. You have some categorical, right? That's how we normally used it before. We have a categorical. You take a one hot embedding, where it's just like a one hot, and then you multiply it by a matrix, and you get a learned matrix, and you get an embedding vector that represents that somewhere. So for a continuous variable, we can do this as well. You can actually do a learn, because nothing's really continuous, but so how many time steps you have, right? And the categorical is which time step I'm on. You can still do that with continuous. And I remember reading the attention all you need paper, which is where I first learned about this, that they said, oh, we tried both ways, and this way, the learned embedding works just as well as this one. This one's faster because you don't have to learn anything. It's deterministic. So what we'd like is an embedding where, first of all, any time step within the range has its own unique embedding. Secondly, it's deterministic, so it's fast, so we don't have to it's always the same. We don't have to learn it. We like it so the time steps that are close together have embeddings that are close together, so that their similarity is dot product, whatever is close to each other, right? So they're not a big change from one time step to the next. And we'd also like these embeddings to be like typical activations that is in the range like -1 to 1, not like, we could imagine, well, let's just put in the number of what time step it is, that's big integer, but then that would be wouldn't solve that part of the problem there. And there's a few other restrictions, I guess, but the common technique for doing this is called sinusoidal embedding, and this is directly from that paper, Attention is All You Need, which introduces the transformer model, but it also is where I first saw, and I think a lot of people first saw this kind of embedding. And the trick is to do a sine and a cosine wave with different frequencies, starting at the highest frequency you could, and then all the way down to some low frequency. And sine waves for even indexes and cosines for odd indexes. So that's basically the idea. And in this formula, I basically goes from 0 to half the dimensions of the model, whatever the embedding dimension you want to have. And there are two, and then there are two waves at each frequency. That's how I have to divide by 2, because there's actually be 2 waves for each frequency, one sine and cosine. And then we just evaluate that as a function of position to get that particular sine wave, and we add them all up together, or line them all together, no big vector, and we have our positional embedding. So again, I think I said this already. This is the same idea as using transform models to encode the token position in a sentence you're typing in ChatGPT, right? The same principles used. So there, they're added to the embeddings, and here we're going to do something different with the embeddings. Let's see, skip all this. So he does this demonstration for how the embedding looks. So he takes so this is just basically implementing these equations, except they think the difference is that he doesn't do, in the paper, they do even, odd, even, odd, even, odd alternating. Or I should say sine, cosine alternating. And here he just does all the sines and then all the cosines, which is fine. It doesn't really matter. Has no impact on the thing. So he evaluates this, and this is what they kind of look like for a few of the sines and cosines. You can see they're 9 degrees out of phase, as you expect, right? In electronics, we call this quadrature phase encoding, because well, one thing you can think of, if I have a sine and a cosine, right? That also defines an angle, right? So you can think of this as being little rotations at different frequencies. And that's kind of like the analogy I like to use for this. This just shows what the embedding looks like. I wrote this thing, amusing analogy, and the idea is that I kind of borrowed this from some other guy's blog post, but then modified it a little bit. And you can think of each sine and cosine pair as controlling the position of a knob. And so the position, the time step, or the position, the token number, whatever you want to call it, whatever you're using this for, you can think of this being a row of knobs, right? So each knob, you need a sine and a cosine to encode that angle in those two real numbers, right? Or vice versa, the sine and cosine determines the position of that knob. And the first knob is a very coarse knob, you go from 0 all the way to 2 pi, and it goes all the way across the entire time step thing, right? And the next one is a little bit finer, so it goes multiple times across. And as you go further and further and further, the knob, a little tiny change of the knob moves the position. I should say a big change of the knob only moves the position a little bit, so you have like a fine tuning control of what the position is. So that's kind of how it works with the sinusoidal embedding. You can think of it this way: we're just encoding the position, all these different rotations, right? And then as we move the time step, the knob to the right and the higher frequency ones spin, 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 and the others go slower and slower and slower and slower. And the configuration of those knobs determines a unique time step. And this also illustrates how one time step is close to the next. If client is very, very close to another one, the embeddings are very close, because most of the knobs are going to be almost the same position. Only the highest frequency knobs are going to be different, right? A lot different. And secondly, you can see the two positions are rotated, or excuse me, two different time steps. Any two time steps are just linearly related by rotation, pairwise rotation of all those knobs. And that was another thing that they mentioned in the attention is all you need paper, that was a desirable property, that the relationship between one position, the other position is linearly related, so the model could learn that from here to here, it's just a linear projection. And since all these deep learning models are a bunch of linear projections with nonlinears on top of them, that makes it easier for it to understand like how far that other token is, or other time step in the model is. Anyway, I don't know if that helps or not, but that was my attempt. And that's how I kind of came to terms with how these time step embeddings work.
Yeah, no, it's helpful.
But just
And
as
I have not read that paper.
Me
Certainly
neither.
familiar with the name. Yeah, being the first major attention paper. Is that a pretty straightforward read, Ron?
It actually is. I mean, it's very straightforward and pretty readable, surprisingly. It's not the first attention paper. It's the first transform paper. The reason why it's called attention is all you need, because people before that started using attention to help fix up their RNNs and their LSTMs, right? They're like, well, my LSTM keeps forgetting stuff in the past. What if we add in like this similarity score thing to try to look back at old tokens way long time ago to help it,
Yeah.
So they added attention to it. Then the big breakthrough was like, hey, wait, we don't need the LSTM anymore. Just get rid of it. Just use the attention. And that was the invention of the transformer, basically.
Yeah.
Hence
Yeah,
the
I guess
title.
I use like sine and cosines for different seasonal effects a lot. Because it's circular.
Yeah. Yeah, exactly. Periodic, yeah. One thing I was trying to remember just now, though, in the previous. Oh, I see. No, never mind. I got it now. I should remember now what's going on. Okay, so that's how we're going to get the time step into the model. I'll skip over these figures that he showed. these are just illustrating what the embedding vectors look like. So on the bottom here is the position, and this is the different encodings. And I guess the point was that if this is your embedding, it looks like you're wasting a lot of space. And he makes this point that if your maximum period is 10,000, but your time steps only go to 100, you're wasting a lot of space down here at the higher frequencies, or at the lower frequencies, I mean, where nothing actually happens, right? And so he said you can fix that by, because having a bigger, and so it just illustrates it with a smaller period. Then you can see there's a lot more different. It's easier to see the differences with two different positions. Positions is the x-axis, and then the y-axis here is just the vectors lined up, right? The embedding vectors lined up. And if I do that same like 32-bit embedding to 10,000 time steps, then we have all this wasted space. We can improve that in two different ways. One, we can just go to a much, much bigger embedding. So I'll go to 128. Now you can see that we can see a lot more of the differences. Still using a too big period. There's a lot of wasted space, but now there's clear differences between adjacent time steps because I've increased the embedding size. Or you could decrease the period. And here's like what it would look like if I really increased the period down to 100, which is actually how many time steps I have, right? I'm not wasting anything. My max period is equal to, there's a 2 pi here, but the max period is equal to the actual period of my time steps. Everything's being used better. There's a link here. I wonder if I can copy this link. Okay, maybe not. Just want the link. Let me just grab this link real quick. I'll put this in chat because there's a really nice little tutorial on positional coding if you're interested in digging into it more. Here we go. Okay. Okay, after all that, what do we do with this embedding? One thing you can do in the transformer is they add it. You could also concatenate it. That's another option. And here, what they're doing, he doesn't really explain why this is what they decided was the best thing to do, but they use it instead to define a shift in a scale to the activations. So depending on what the time step is, they're going to do a learned shift in a scale of the embedding of the activations for that particular layer in the UNet. So they take the embeddings and then they go through a projection layer from the number of embedding inputs to twice the activation outputs, because we need two vectors here, one for scale and one for shift. And then they chunk it into two parts, and then one part uses scale the activations, the other part uses shift the activations. That's basically what he does there. For more on that, you can see the actual code in the notebook in the embedded res block, as it's called now, right? In fact, we could look at that real quick. Oh, here it is. Yeah. Where is it? Actually, here it is. It has the attention here too. We'll get to it in a minute, but how the attention gets added in. But the embedding is here. The embedding's here, and then the embedding's here. Now all we do is use a linear layer projected into twice the number of features for that layer, and then he uses it in the forward thing, to do a scale shift here. That's it. That's how the embeddings are used. Why this versus adding or whatever? I don't know. Maybe I guess this is what part of the answer is. This is what Stable Diffusion does. So okay, but
I have maybe a question you don't know the answer to, but do you know why they call embeddings rather than basis?
yeah, well, I think the reason why they call that is because you think of like you're taking whatever your variable, whatever like let's say you have I'll always go back to the categorical thing, which is how I learned about embeddings, right? So let's say I have 10 categories. I could code those up as just like 1 through 10. I could code them as one hot. If I use an embedding, I'm saying I'm embedding these categories into a bigger vector space. So as vectors in this bigger
Well,
space.
I guess like the vocab, like using the word embedding versus a basis expansion. Because like my
'Cause
understanding
they're
of
not
the
based, they're not
history of
orthogonal.
embeddings is
Yeah.
that it's the past values of the internal states. Like from dynamic systems. Anyway, this is probably like I'll just dig into it.
Yeah, I'm not sure. I don't remember using embeddings in dynamic systems in that way, but And here, the embedding is just the idea that you're taking this thing and putting it into a higher dimensional space, embedding it into.
Yeah, so we call that basis expansion.
Yeah, I mean, you can certainly call it that too. Yeah.
Yeah,
But we're not spanning that space with these vectors. So it's like it's some subspace, right?
yeah.
You're only spanning because your dimensions of you think your embedding is usually much smaller than the space. So it's a subspace that you're spanning. So in that sense, I guess is why it's considered embedded in there. I don't know. I don't know. You're right. I don't know the answer. Let's go back to that idea.
Yeah, I mean, I asked AI that question and it did come up with a response.
Oh, what did it say? I want
Says
to hear.
while both basis expansion and
Oh,
embedding are used in machine learning to represent data in a higher dimensional space, the key difference lies in their focus. Basis expansion primarily aims to capture nonlinear relationships within a given data set by transforming the features into a combination of basis functions, while embedding focuses on representing complex entities like words or images as vectors in a lower dimensional space that captures their semantic relationships.
Mm,
Essentially,
okay, I
basis
see.
expansion is about feature engineering, while embedding is about creating a meaningful representation of data points in a new space.
Okay.
I,
yeah.
Yeah, so I
let the
guess it's
helper.
just from the
It doesn't.
language
Yeah, it doesn't
language
answer.
modeling.
Yeah, it doesn't answer your
Yeah.
original question, which is why the word embedding was chosen for that. I do not know. Other than thinking like embedding it, sticking it in that space, But
Yeah, yeah.
somebody used it and everybody else started using it. Probably. I
Nice.
don't know. I've used it so much. I've kind of just like it's one of those things like, oh, why is it called a rock? I don't know.
Getting to just an earlier point you made, Ron, you noticed like throughout the video, Jeremy's like all this stuff is kind of ad hoc, right? Like just a lot of the design choices, just the
Yeah.
number of time steps I think was 10,000. He didn't he didn't like a lot of that. Like
Well,
bothered him, right?
yeah. So the 10,000 is a magic number from attention is all you need. That's what they use because
Right.
that's the size of their context window. And it's weird because 10,000 is not even the period because it's 10,000, 10,000 divided by 2 pi is actually the period, the maximum period. So that's kind of weird, but yeah, anyway. Yeah, it's just like they just used it and there's too many choices in some ways, right?
Yeah, yeah. Someone makes an artistic
Yeah,
choice and then
yeah,
people just kind of copy it,
yeah.
right?
It's like I'm
Yeah.
gonna use 10,000. We should go back and revisit this later. Oh, late, everything's working. Forget about it. We're good. Publish.
Yep.
Yeah,
Exactly.
probably forgot about that number in there, right? I know that happens to me all the time. I'm looking through my code. Oh crap, I forgot about this magic number I was gonna change later. It's been sitting in here for a year. Yeah. So it's always good to do a good, careful code review, I guess. But anyway. So the next topic was attention. And this is at 48 minutes in, so you can see that oh, we're not going that much faster. So we'd be going faster than him. We got to go faster because he took 2 hours for this, so I got to speed up. The attention, he says we're going to use attention for 2 reasons. One is, well, that's what they use a stable diffusion. He says, well, so he's going to use it here because that's what we're doing. We said we're going to do stable diffusion. But he does say he didn't see any real significant improvement. He just wanted to warn you that there's no real significant improvement from adding attention to this model. And I skipped over the part. So he used this thing we just talked about to train and sample, and he got pretty similar fit scores that he got from using the built-in stable diffusion model from Diffuser's library that he demonstrated one of the previous. I don't know, it was last time or the time before, I forgot already. But so already we're getting the same kind of fit scores within significant errors from that stable diffusion. I guess it's a stable diffusion without latent, because I can't believe it can do as well. Well, for MNIST, it probably doesn't matter. For fashion MNIST, it probably doesn't matter that you're not doing latent diffusion. So that's probably why attention doesn't matter either. It probably doesn't matter for these small images. It probably matters a lot more for bigger images. So in any event, that was just one reason. The other reason is that attention is a key component of transformers like GPT, which he says we will see later in part 3, presumably. But as far as I can tell, there is no part 3. It never materialized.
No, you just wonder maybe that will come to be at some point after he finishes that new thing he just introduced
Yeah,
like a couple months ago.
yeah. Well, the new thing has to do with using language models to help you write code, right? Isn't that what the whole thing about?
Yeah, it seemed more applied.
Yeah, applied. Yeah.
less theoretical, but that's not, unfortunately, it's completely private at this point.
Yeah.
I don't think he's released any of the lectures or whatever.
All right, so where was it? Oh, yeah. So the idea of using attention is kind of like I hinted at before, is the idea that we want to say, hey, like in the language model, the idea is, hey, let's reach back to these older tokens and find out if they help us figure out what's going on with this token. And the same thing is true here with the image. Now we're going to say, let's reach over to this pixel, or in the emitter layers, let's reach over to this feature on this pixel. I guess called a pixel, but it's not really the image pixel anymore. It's a inner layer representation of the feature map, or whatever you want to call it. But it's called a pixel. We're going to compare this pixel to that pixel and say, hey, this pixel could affect what I should be doing in this pixel. And so we're going to use attention to do that, because that's exactly what attention is good for. In the video, he talks about, like, well, this, if you have a picture of a cat, whatever this, if there's an ear over here, that's got to affect the way this ear over this it should look too, right? They should look similar, and then so I should be using whatever I'm doing with that ear to help me inform what this ear is going to look like in terms of like image generation. But what attention actually is relatively straightforward. All it is a weighted average of the features at all locations in the image, where the weights are determined by the similarity of those features at those different locations. So how similar that feature is to my feature determines how much weight I should put on adding those features to my features of the pixel I'm looking at right now. That's the basic idea. And for this, we use a 1D attention. So we're going to flatten the image out so that we don't care about the height versus width. We're just going to multiply height turn width and just have a big long one line of the image all flattened out like that. And so then the weighted average just looks like this. The pixel at the feature at x sub I will be equal to, well, we're going to add in x sub I to itself, this little residual connection again, but otherwise it's a weighted average of all the other pixel features, where the weights are going to be determined, like I said, by the similarity measure. And if we write this as a matrix equation, it's just x equals x plus wx, but the wx is the key part. And to do the similarity, we're going to use a dot product, which if you expand that out, becomes an outer product, right? Like this XX transpose. So this takes a feature map, which is pixels. I'm going to say pixels, but again, they're not pixels. Pixels times features times another one is features times pixels. Or sorry, I did it backward. Pixels times features times pixels multiplied by another matrix, which is pixels times features. I don't know. I got that. I can't do that in my head. You know what I'm saying? In the end, we end up with a pixels by pixels map, where the intensity of those different pixels by pixels map. Remember, these are the whole line image stretched out, so it can height times width times on one dimension, height times width on the other dimension, and the intersection tells us how much we should weigh in that particular feature into our feature, right? So, and then we need to normalize those to probabilities, and we use softmax for that. That's basically the whole idea of it. I hope that was clear. I mean, it's hard to describe in words, but in the video, if this is not clear, which it probably isn't, go back to the video, because he does do a pretty good job, I thought, explaining that, except at one point he gets the rows and the columns mixed up in the multi-headed part. We won't worry about that, because I just did, so it's easy to do. But so that's basically it, except we don't want to use X, because that would be the same for, we want to learn different things from different parts of the feature map. So what we're going to do is we're going to take each X and we're going to multiply by learnable matrices called query, key, and value. I don't know why I use N there. I think I meant to use a V there. And so so the attention now becomes this, which is just this thing with these new matrices multiplied in. So we're going to take the vector X, multiply it by the key matrix, transpose it, and multiply it by WQ times X to determine this self-attention, like how much we should pay attention to that feature, because of how similar it is after linearly transforming it, right? And then we multiply that times, then we do this part, WX, which is just now, this is the weight matrix. This whole thing right here is the weight matrix, softmax of this. And the thing we're going to multiply by is this value matrix, which is determined by this learnable matrix times, again, by X. And that's what the self-attention looks like. And these you don't usually see this written out this way. Usually it's written this way, Q, K, and V. And you're supposed to know that that's how Q, K, and V are formed by these linear projections on the features. And there's a scaling here. because when we do this multiplication, we end up with things that are going to be too big. So have to rescale them back down. Yeah, let's see. The only other complication is multi-headed attention. What are we doing a time here? So we could look in the notebook to see how these things actually look. If we go through really quickly, this is the notebook that he provides. So we just going to generate a random, this is a 16 by 16. Wait, do I have that right? Channels, features, height and width, right? I just forget where it's supposed to go. Does anyone remember what this channels features? This must be, sorry,
That's batch size.
batch size, channels, height and width, maybe?
That makes sense to me.
Yeah, that's right. So batch size, feature channels, height and width, and then we're going to flatten it. That's all this does. It's going to flatten it down. So it's batch size, the height, and he changes the order of them because that's, I forget there's a reason for that. So this is now the flattened 256 pixels, and this is now the features at each pixel. So now they're just one-dimensional vectors, except for the, and there's 32 of them, and then there's a batch of 64 of them. And so these become these literal matrix projections. They're just, and so if Ni is the size of our, what it is, right? The size of our feature map, then we generate all these linear projections. We project them to get the KQ and V. We can just calculate this KQ transpose. And sure enough, like we said, we get something that's pixels, number of pixels times number of pixels, right? And 64 of them because that's the batch size. So he then defines this self-attention module, just putting all that together. And the details are here. We take input vector X, right? Matrix X, which is, here we go, batch size, channels, height and width, right? That's the shape of it. There's a normalization layer here, or that group norm. And then reinterpret this as a one-dimensional line instead of a two-dimensional image, calculate the QK and Vs from the learned projection matrices, calculate the weight matrix, I guess before softmax, this he calls it S matrix, do a softmax on it, determine the probabilities, and then do a projection on that, right? Oh, here it is. Oh, sorry, where's the? I guess I left out the fact he also does a final projection on X at the end of all that. So this is the project. This is X being projected to the value space. Then this multiplication happening, right? But then he does this final projection on X, the output projection. So that's another part of the self-attention model. Then reshape it back to an image, and out it goes, but with a skip connection. That's it in a nutshell. Now, we don't want just one of these heads because it only will, they tend to be pretty focused. The softmax is pretty sharp, so it'll end up only focusing on certain features and not, you'll learn to focus on some particular feature, but we want to be able to focus on multiple different features. So he introduces this idea of multiple heads, and just checking the time here, I'll better move along. This is just checking everything works. Multi-head attention. This is something I added. This text wasn't in there. But, so this is actually not difficult, it turns out. All you got to do is take your input features and split them into small chunks, right? And then do a separate head on each chunk. That's basically all there is to it. And then put them back together. And that's all the multi-headed thing is. And it doesn't even look like much happened at all. And the trick, the way he does it, is so that he doesn't have to write multiple heads. He just uses one head, but takes the different chunks and temporarily transfers them into different batches. So he fakes it not fakes it, but it's kind of a cheat in some ways, or a trick. Trick is a better word, not a cheat, not a fake. The trick is to expand the batch to include these different chunked up inputs, then run the normal self-attention, and then take it back apart. So the details are in the video, but that's the basic idea. This is what this is trying to explain here. Heads to batch, batch to heads process is doing there. But So that's the trick there. There's a little digression on INOPS, which I'm not going to go into because we're never going to make it to the end if I do. But I think it's interesting and worth looking at.
Yeah, I just briefly scan that section or listen to it. So it's like an adaptation of the notation that we learned
Yeah, the I something.
earlier.
Yeah.
Yeah.
Yeah, it's a generalization of that to do more things. And it's kind of cool that it does allow you to easily, reshape things and however way you
Yeah,
want to.
symbolically, right.
So we have like, and the batch size, the features, the height, right? No, wait, this is the heads. I'm sorry, the thing's already split. Uh, yeah. What is S? S must be the number of features, right? And D must be the number of pixels, I'm guessing.
That dimensions.
Yeah,
Is
number
that
of
what the D
dimensions.
stand for?
Yeah. So he just reshapes it. So now we're going to increase the number of batches by the number of heads. So we're going to have heads times more uh, batch uh, samples in this batch, right? But we only have a single head now in the model. Excuse me. Anyway, so this self-attention multi-head is basically exactly the same as the single head attention, except for this part right here. We do the heads to batch and chunk this part right here. Another trick he introduces, rather than having three separate linear projection, he just has one big one and then chunks up at the end. So that's, to me, that's kind of pedagogical error because you're complicating things unnecessarily, but that's fine. So he had three separate matrices. He's, oh, I'm going to make one matrix, then chunk it back up because he loves chunking things. So we're going to chunk it up. So but that's a change, but not a real change. Um, this is exactly the same. This is exactly the same. And then we split it back up and everything else is exactly the same. So really two changes, that chunking it up. Oh, and then the other thing is we have to change the scaling a little bit because each head is smaller now. So that's it. That's it. It's pretty cool. Okay. Oops. Yeah. So that's, nope, where'd my thing go? Here it is. I don't know, hopefully that helps understand how that works. Hey, we're gonna make it to the end, I think, are we? No. Yeah, we are. Have confidence. So then he uses this in the diffusion model, and I'm not going to go through it either because I only have time to do the final thing, so I'm just going to kind of skip through this. So he adds the attention to the fusion model in a very straightforward way. I'll just look at it real quick. That's it. Yeah. So he just adds it in. Okay, if you want attention, tell me how many attention layers you want, and tell me when you want. Well, okay, I guess I should go up to the next level. Here's the model, right? So tell me how many attention channels you want. And tell me which layer to start the attention on, because if I shouldn't start at layer 0 because the model will get way too big. If that, even with the 64 by 64 images we have, or 32 by 32, what are they? Anyway, the image will be too big, and they'll require too many. The model will be too big. So he starts at 1, the next layer in, when the model's been downsampled a bit. And so this UNet model is the same as before. We had the same embedding before. The difference now is that if we want to have, well, this is the upper level thing. So it just adds in all these sequential layers that have the down blocks and the up blocks, right? That's essentially what's in there. Passed into there is the up blocks and down blocks made out of these res blocks with the upsampling for the up block, right? And for the down sampling for the down block. I'm just going through this very quickly, but you get the idea. The key magic happens here in the res block itself, which now has the possibility to have attention channels. The default doesn't have it. And the only change we made here is if there's attention, then do it, right? Have a self-attention module. And then when we pass forward, everything else is the same. Here's where we put, we pass everything through the model. Then we do the scale and shift from the embedding. And then if we want attention, okay, just pass it in attention and add it on. That's it. So it seems like a lot of, it's kind of crazy how easy it is once you got the code for this self-attention module, you can just throw it in there. Yeah, okay. Anything I'm forgetting about? Nope. This right here is the residual connection from the other layer, right? If there is one. Okay, then that was the quick version of that. Then the next thing he does talk a little bit about transformers. He say, hey, at this point we actually have everything we need. So now when you go back, you can go look at that attention is all you need paper. You should be able to understand it. You have everything you need because all the transformer is these attention layers followed by ordinary MLPs, right? Feed forward networks, right? So the essentially what he says is the attention layer does a mixing of different positions. It also does some mixing of channels, but mostly does mixing of different positions. And then finally following that by the MLP does a mixing of different channels at that particular pixel or at that particular position for the language model. And that's all that's in that, like the normalization layers, we already know about that. And the residual blocks, we already know about that. All that's all that's in that paper. So it's pretty, should be able to understand it. They use sinusoidal position embeddings, just like we talked about, except they add them instead of doing the scale and shift thing. And he says it turns out the transformer has been shown to be extremely flexible. So there's something called a vision transformer, which has been very successful. So remember back a few weeks ago or a few lessons ago when he was comparing his model with other models on that Papers with Code website? Well, the top scoring ones,
Yeah.
he skipped over because they were using pre-trained models, but they were all transformer models. And the pre-training part's important. It turns out a transformer can really learn to do much better than a convolution network, but to do that, it requires a lot of data. And that's why all these transformer models are pre-trained, even in the GPT. The P stands for pre-trained in the GPT, right?
Right.
Because they pre-train it on just next word prediction, and then they later go back and do the fine-tuning on the particular thing they're trying to get it to do. And so that's exactly what they were doing in the Papers with Code thing. They had pre-trained this thing on large amounts of data, and then they use it to fine-tune it for the particular problem of that image generation. So that's basically that. Oh, there's also this kind of cool, the illustrated transformer. Should give you that one too. Another nice reference for transformers, because we won't be learning about transformers in here beyond what we just did. Just to show you what a transformer, this is from the lecture. He shows you what a transformer block is, so you can see it in all its very little glory. All the magic is hidden in this self-attention block, where you get the idea. There's not much to it. Do attention, do an MLP. The MLP is just linear activation layer, right? Layer norm and linear. That's it, right? Multi-layer perceptron. So the forward layer just does the attention. Oh, here we're doing scale and shift because we're doing, I guess scale and shift must work better for vision models than or for image models than adding scale and shift and then an MLP. That's it. And then residual. That's the whole thing. Now there's more in the paper because the paper is doing language models and it's doing like a encoder decoder type situation. But these are all things we should be able to understand, I think. Okay, how are we doing? Oh, we're doing good. So
Yeah, pretty good on 10.
149 in the video. We're at 48 and we're an hour ahead now. We've gained back the time. Yes. So the last subject is the conditional model. So he's going to use the learned. I'm sorry. He's going to use the what am I saying here? Use a normal learned embedding. Oh, right. So, so we're going to have to add, now we want to train the model to recognize which class it is, right? We're going to tell the model when we're training it which class is involved. So that when we get later, we can put that in and it can generate an image from that class. And to do that, all we need is another input to the model. The other input we're going to have to embed because like the 10 different categories or whatever there is. We're going to embed that into a higher dimensional space with a learned embedding this time, kind of a traditional embedding, not a science-oriented embedding, just a traditional embedding that we'll learn. And that will be just, it turns out what he will do is just add that to the time embedding and then use it to scale and shift just like normal. And he trains well, he showed. Then the sample we also again have to pass in the class and most everything else in the model is all the same. So I did, this one I did do. I tried training it. My GPU only has 8 gigabytes, which I thought was plenty for playing Flight Simulator, but not for training vision models, I guess.
Yeah.
So it totally filled up and it was able to train, but only for like 5 or so epochs. And then when I pushed it beyond that, it was a mess. So I moved it on to paper space, which I hadn't used for a while. So that was a big struggle because it doesn't have conda and I had trouble getting all the dependencies to work. But I finally got it working. I ended up doing 25 epochs in the end. And it seemed to work. So I'll just show you that real quick and that'll be the end. Just in case we run out of time, I'll say, what's the summary? We did everything in stable diffusion except for latent diffusion, which I don't know if we're going to do. I think we're going to do that next lesson. And passing in full sentences, I know we're not going to do that. So, because that requires having a full language transformer. So let's find that thing. Here it is. So I'm not going to evaluate the notebook. We talked about most of these things already. The only difference here is, actually, I think I just probably, is that the right one? Yeah. Blah, 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 moving on down. Here it is, conditional model. So the difference with the conditional model is we passing in now, where's the forward method? We're passing in now the image, the time step, and now the class in there. And we're training it by doing the time step embedding we already talked about. Then this learned embedding, which is up here, right? Just an ordinary embedding module from PyTorch for the end classes with the same embedding dimension as the time step. Add them together, and that's being used to do the scale and shift somewhere in here. What level are we at? Oh, we're at the full model level, right? So once we do that, we pass that in through all the modules and inside the actual modules. Actually, you can't see because the actual modules don't different. So if we're using the same modules we used before, because once you have the embedding, the other modules don't know anything about where the embedding came from. So all the other modules, all the lower level modules, the ResNet module, and the up sample, the down sample, which are made out of the ResNet modules, those are the same. Everything else is the same. All we got to do is pass in this embedding to condition it. And so set up all the training stuff, 25 epochs. I did 1 epoch on here just to make it work, but on Paperspace, I did 25 epochs. And what I ended up doing is just saving the thing so I can load that back in. You have to do it as a state dict, not as a full model. It wouldn't work for some reason. I don't know why. This worked, and the other one gave me an error I didn't understand. So I'm like, okay, forget about that. But it was something I couldn't pickle something. I'm like, okay. I asked ChatGPT, I said, do this instead. I'm like, okay, I'll do that. That's what I did. So using that, we can sample everything. Even the sampling is all the same. There's no real difference other than having to pass in the class. Here it is, see the class. So I have to pass that into the model here, right? We're doing the sampling. And so mine don't look as good as his, but they kind of work. So here's a t-shirt. Showing me a bunch of t-shirts. Some of them look a lot like t-shirts. And this, I don't know what this is. This is like an 80s skinny girl, something. I don't know what that is.
Wow.
So, and this, it's definitely not a t-shirt. So I don't
Looks
know.
like
Mine,
a zombie costume.
yeah. So mine didn't work as good as his. I don't know. I don't know why. I just did 25 epochs. Maybe he did more. Although I thought he did 25, but luck of the draw. I don't know. Maybe there's an error somewhere in my code.
Or maybe there's a error in his code.
Yeah, this is even worse. And then ankle boots, I mean, I guess, right? Could be not the greatest, but yeah. So it basically works. So the lessons I learned from that is that don't use your GPU for training these. And I'd really if you want to use a cloud provider, just be aware that it's going to take some time learning how to get things to work on there. And if you haven't used it for a while, it's going to take time to learn it yet again. So that's what I found. So that's basically it. We did it. We got all the way through condition generate. Now we can generate something from fashion MNIST. So we really need, computer generated boots of low resolution in black and white. We got that solved. Somewhat. Even that's not that great. I guess we could train it more, but yeah. So that's awesome. We're only one away now from finishing this course.
Yes.
So I'm looking forward to that. And Aaron, you're doing that next week, right?
Yeah, I'll handle that next week.
Does anyone have any closing comments before I hit the stop button on this?
No.
I don't think so.
Well,
No, this was great.
Just,
Thank you.
yeah, great job. This is